Okay, let's get started, please. So today we're going to enter a new chapter. This has to do with orthogonality. Orthogonality, or some sort of geometry. So 5.1 is about the scalar product in Rn. The scalar product in Rn, that's to say the dot product. Later on, we're going to do something called the inner product, which is a generalization of the scalar of the dot product. So it'll be, you have vector spaces, and then you have something called the inner product of it. The scalar product is your first encounter with your first encounter with something that is an inner product. 5.1 is stuff that you should be familiar with from Calc 3. So I'm just going to go through it kind of quickly. So 1, the dot or scalar product. In Rn, you have x and y, two vectors normally you think of them as vectors, but we'll think of them as n by 1 matrices. The scalar product is defined, or say their scalar product is defined as x transpose y. Right. So x transpose, right? X transpose is a 1 by n, and you're taking a 1 by n times an n by 1, and you get a 1 by 1. Right. You get a 1 by 1 matrix, where the entry is, of course, x1, y1 plus x2, y2 plus xn, yn. So this is the dot product in Rn. Are you okay with that? The dot product
yes,
in Rn. Okay, very good.
Trust you.
Okay, very good. Yeah, but you shouldn't.
I shouldn't.
Yeah, well, I don't know.
Back to John Stewart.
No, not for any sort of philosophical reason, but because I'm not sure if this is okay with you.
Okay.
Are you okay?
Oh.
Right.
Yes,
So
I'll think about it.
So we have something called the dot product in Rn.
Yes.
The dot product. You have two vectors. We think of them as matrices. Right? They're n by 1. They're column matrices. Okay. And then we have this thing called the scalar product, or the dot product. And you get that by taking the transpose of one and multiplying it against the other.
Okay.
And you get this thing.
Okay.
Okay. In Rn, one has a relation of the scalar product with magnitude of vector, right? Right. I'm talking about the magnitude of the vector that's related to the scalar product by what? How do you express the magnitude in terms of the scalar product? Just to review, what's the relation between scalar product and magnitude? Yeah.
X transpose x.
X transpose x, right? So it's going to be x transpose the scalar product of the thing against itself, and then you take the square root of that. Right? You take the square root. You take x transpose itself. You take the square root of that, and you get the magnitude of the thing, right? So the scalar product is related to magnitude in this way, and thus one gets a relation with distance, right? The distance from x to y, if you have two vectors in space and you want you have two vectors and you want the distance between them, right? That's the magnitude of the difference, right? That's the magnitude of the difference, and so you take that, you take the dot product of x minus y against itself, right? So there's a connection with magnitude, there's a connection, once you have a connection with magnitude, then you have a connection with distance. And then there's this thing called, you have a geometric interpretation of the scalar product, namely that the scalar product of two vectors turns out to be the product of the magnitudes times the cosine of the angle between them. Okay, so this is like what the scalar product represents geometrically. And this fact is based on the law of cosines, which is itself a consequence of the Pythagorean theorem. Okay. Other things that I think you're probably familiar with. There's something called the Cauchy-Schwarz inequality. Does anyone know the Cauchy-Schwarz inequality? Anyone know the Cauchy-Schwarz inequality? No? Anyone heard of the Cauchy-Schwarz inequality? No? Okay. It's in any case, it's pretty straightforward. That if you take the absolute value of a dot product, you take the absolute value of the scalar product, then it's controlled by the products of the magnitudes. It basically gives you a size bound, a size control. Yeah, Mia.
I'm sorry, what do you, size control? Oh,
Yeah,
okay.
yeah.
Wait,
So like
never mind.
you have one vector. You have one vector dotted against another vector, and it tells you something about the kind of number you can get out. The only numbers you can get out are that the dot product is controlled by the product of the magnitudes. Okay. And even if you haven't seen it before, that should be, at this point, it should be now obvious because of. Why is that fact obvious? Because of the previous statement, because of the previous fact, right? The absolute value of this is going to be equal to the product of these things times the absolute value of the cosine, right? How big can the cosine be? 1 at most, right? So this thing is smaller, right, than the product of the magnitudes. This thing in absolute value is smaller than the product of the magnitudes. Okay, so that's the Cauchy-Schwarz inequality. Okay. At least for now. Okay. Okay. Everyone all right so far? Everyone all right? Okay. Okay. So other things that I'm hoping you've seen before. If the scalar product is 0, we say x and y are orthogonal. Right? We say that these guys are perpendicular to each other. Right? And that makes sense because of the geometric interpretation, right? That's going to happen, well, assuming the things are non-zero vectors, that's going to happen when cosine is 0. Right? When cosine is 0, in other words, they are perpendicular to each other. Okay, so that's what we call perpendicular. Okay. Okay. And then the last thing that is recalled in this section, the last big thing that's recalled in this section is the notion of vector projection. So call vector projection of one vector onto another vector, where the projection of x onto y is turns out to be given by the following formula. Okay, right. So the picture is like this. Right here is x, and here is y, and you're wondering if you take that x vector and then project it perpendicularly down onto the sort of y-axis, right? If you project it down onto the y-axis, what is that thing, right? What is that thing? Let's say that y is here. Okay. You'd like to know what the projection of x onto the y-axis is, and it turns out which you can figure out using trigonometry. Right? You figure out using trigonometry. It turns out to be a certain multiple of the y direction vector, right? What multiple? Or it turns out to be this multiple. Using trigonometry, it's easy to see this. Okay. You could. It may at some point be convenient to write it as follows. So I'm just going to combine these two guys together and get magnitude squared. Right? This thing is magnitude squared. Right? Y transpose y is magnitude squared. So I'm just combining these things together and leaving the y out. So x transpose y over y transpose y, y. Any questions? So these are all things that I hope you've seen before. They can be done in R2. They can be done in R3. These are all can be extended to Rn. The section also contains some other things, like finding the equation of a plane and this sort of stuff that you've probably seen before, but even if you haven't, it's not that important. So I think the most important stuff in this section is just to remind you of these facts. Okay. Okay. Who are you guys? No, just kidding. Okay. 5.2. Orthogonal. Sometimes I forget, actually. Okay. Orthogonal complements.
Like with Calc 3 or like where you're
Yeah, sort of. Like.
more like a philosophy?
Yeah. Yeah. I guess after you teach for however many years I've taught, then it starts to get.
Do you ever turn around and you're like, oh, I forgot there was people here?
No, that's never happened. But it's sometimes you're right. It is sort of like waking up from a dream. Right? Like you're talking this way and then you turn around like. Oh yeah, people. Yeah, I guess yes. Okay, so the answer is yes. Yes. Right, because you're concentrated, right? You're focused on something, and then you. Right. But I'll tell you something sort of related to this. When I was an undergraduate, the classes could be pretty small, so they could be like 3 people in a class, say, in an upper level class. There was one class taught by the mathematician Dwork, DWORK. It was something on like periodic analysis or something like that. Some high-level course that had only three or four students. One day, one girl, I forget who it was, decided to go to class, happened to go to class late. She was 20 minutes late. She came in and she found that Dork had been lecturing to an empty room for 20 minutes.
He walked in and didn't even...
It's not clear.
Okay.
I'm still hoping that I can pull that off at some point.
So we just
So
don't
on
show up.
Friday.
Yeah, next month.
Yeah.
Monday.
Wait, I have a question.
Yes.
Do we have class the Wednesday before Thanksgiving?
I'm afraid so.
Okay.
But it will be online, so if you want to skip that class, it's not a great loss to you.
Okay.
That is, I certainly don't mind lecturing to an empty class while recording. I guess I do kind of mind.
So I think I'm going to give you guys 2 minutes to do this. To empty class.
Walks outside.
Yeah. I guess I mind a little bit, but I could do that. Is there another question? Okay, so here we go. Orthogonal complements and direct sums. Okay, now let's do something. Okay, so we'll start off with something that's not really the full-blown definition. Suppose x and y are subspaces of Rn. Okay, and suppose that for every x in x and every y in y, one has that they are perpendicular to each other. Okay. If that happens, then we say that x is perpendicular to y. That x and y are orthogonal subspaces. So every element in the first space must be perpendicular to every element in the second space. So here's an example. If in R3, x is the span of 1, 0, 0. Okay. So x is the span of 1, 0, 0. Y is the span of 0, 1, 0, 0, 0, 1. Okay. Right, so the picture is that x is the span of x is the x-axis, right? And y is the span of the other two. So y is the plane, right? The yz plane. Here's x, and here is y. And those guys are perpendicular to each other, right? Because anybody, you can see it algebraically, you can see it geometrically, right? Anybody in here is perpendicular to anybody in this plane. So, do you want to get it? Okay, so another, let's say that x is the span of 1, 0, 0, 0, 1, 0, and y is the span of 0, 1, 0, 0, 0, 1. Okay. So pictorially, right, one guy is the xy plane, and the other one is the yz plane, right? That is not an example. Okay, so here's a non-example. Right, x and y are not orthogonal to each other. Yes?
Is that because of the origin? Because they share a point? Or
Well, no, because the origin technically is perpendicular to everybody, because if you take its dot product, you still get 0.
okay.
Okay, but it's rather because, well, why isn't it? Can anyone tell me why these guys aren't perpendicular to each other?
Can you do on the like vertical plane something at an angle, and then on the other one something like this, and then it would be perpendicular?
So on the vertical plane, something at an angle,
Yeah.
and then on the horizontal plane,
Just like, I mean like flat, and then they would be perpendicular to each other.
like this.
Other way, like on the other axis.
This.
Yeah. Sure.
Yeah, I think that works.
Or like if it followed that axis that the vertical plane. Yeah.
Yeah, even more clearly.
Yeah.
Yeah, or even more clearly. I'll use both of them at the same time. Right. It's not perpendicular to itself. Right. There's some overlap. Okay. Okay. More sophisticated example. The null space of A is perpendicular to the column space of A transpose. So let A be a m by n matrix. Okay. So, right, let's see how this works. Why? Let's say that x is in the null space of A, right? That is to say, AX is equal to 0, right? The 0 vector. Right? So what does that say? That says that if I take then I get if I take A times X, I get 0. Right? So what does that tell me? That tells me that that x is perpendicular to every row. Right? That tells me that each row times x is 0. Right? For all n. And that tells me that x is perpendicular to any right, right? X is perpendicular to any vector in the row space. To any vector in the row space of A. That's to say, perpendicular to any vector in the column space. In the column space of A transpose. Yeah.
The vectors of the row space
Are the
are the column space?
the column space of the transpose.
Oh, okay.
Right,
Yeah.
the column space of the transpose. Okay, so, okay. Okay. Going back to the first example, if I look at, say, well, first, is everyone okay with that? Is everyone okay with that last example? Okay, let me go back to the first example and change it a little bit. 0, 1, 0. Okay. So here, the first guy is the x-axis. The second guy is the y-axis. Okay. So certainly these are perpendicular to each other. These are perpendicular to each other. Is y the collection of everything that's perpendicular to x? Is y all that is perpendicular to x? If we're in space here? Is y all of it? No, right? There's actually more that's perpendicular, right? In fact, this whole plane, as we saw when we looked at the first example, right? Anybody in this plane is perpendicular to x, right? So to say that these guys are perpendicular is not to say that one is all that is perpendicular to the other, but just that if you take things in each one, then they're perpendicular to each other. Okay. For that other concept, we have a different term. Okay. So. If let S be a subspace of Rn, we denote by S perp the collection of vectors in Rn such that xt s equals 0 for all s in S. Okay, and this thing is called, S perp is called the orthogonal complement of S in R. Okay, the orthogonal complement of S in R. Okay, so for example, right, if we were back in that case, right, if this was X, then the orthogonal complement would be the YZ plane. Right? This thing here would be X perp. Okay, because that's all everything that's perpendicular to everybody is X. Right, so it's a collection of you have some subspace, and then you look at the things for which you look at those vectors which are perpendicular to everybody in the subspace. Right? You have a subspace to start off with. You say, who is perpendicular? I want to find the guys who are perpendicular to everybody in your original subspace. And the collection of those guys is the orthogonal complement. Okay? Okay. Sorry? some trivial observations. First, or 0, of course, S is orthogonal to its orthogonal complement. Right. Sort of along the same lines, if S1, let's say, if what notation did I use? If X and Y are perpendicular to each other, then of course, you know, X is in the orthogonal complement of Y, and Y is in the orthogonal complement of X. Is that clear? That I hope that's clear. You know, that should be completely obvious. If X is perpendicular to Y, then what can you say about the intersection? Something being the intersection would have to be perpendicular to, if something is in the intersection, it lies in X and in Y, right? So that would mean that the thing would be perpendicular to itself. In other words, the thing is 0, right? So if they're perpendicular, then their intersection is the 0 vector. Also easy to show. Y perp is a subspace. Right? What would you have to show? All you need to show is that if you have two things in Y perp, then their sum is still in Y perp, right? And any scalar multiple is still going to be in Y perp. So I'm not going to do it. Okay. Where are we headed with this? He's like, what's he doing? Why is he going this way? What we're going to show ultimately is that one thing that will be useful is that given any subspace, you could take Y perp, you could take its perpendicular complement, and then what we'll see is that you can decompose the whole space into some sort of a sum, what's called a direct sum. So we'll see that if you have any subspace in Rn, then you can realize Rn as some sort of sum of these orthogonal complements, okay, and that'll be handy. But yeah. Okay, so right now let's do something called the fundamental subspaces. Okay, so here it is. Given a matrix, that's an m by n matrix, then the null space, the null space of A is the orthogonal complement of the range of the transpose. So the proof goes like this. Let's first show that if you're if you're in the null space of A, then you're contained in the complement of the contained in the orthogonal complement of the range of the transpose. Is it clear what I mean by the range? The column space, right? The column space. Right, because what's the column? The column space is all linear combinations of the columns. That's the same. Right? If I have some matrix. The column space is going to be the linear combinations of all the columns. That's the same thing as saying the collection of outputs when you apply this to vectors, right? So it's the collection of outputs. In other words, the range, right? Just like in the sense of functions. Okay. So okay. So why is it true that if you're in the null space of A, then you are in the orthogonal complement of the range? Why is that true? Mia?
Is that the row space? Is that what did we just talk about?
That's exactly. What did we just talk about? That's what I should say. What did we just talk about? That's exactly what we just talked about.
That the null space of
Yes.
A is perpendicular to the column space.
Yes, that's exactly what we just talked about. So we just did this. Okay.
Is it just the same proof for the null space of A perpendicular?
Yes, right. We just said that the null space of A was perpendicular. The null space of A was perpendicular to the column space of A transpose. Right? We just said that. We just showed that the null space of A was perpendicular to the column space of A transpose. Right? Well, that tells us that, so an A is contained in the orthogonal complement, then, right? Because what's the orthogonal complement? The orthogonal complement is everybody who's perpendicular to everybody in here, right? Well, these guys are perpendicular. Everybody in here is perpendicular to everybody in here, right? So it may not be the whole thing. There may be more than that. Okay, there may be more in the orthogonal complement, but at least we know that the null space is contained in it. Okay. Is anybody confused? You all look kind of confused. Wait, Henry, yes.
Just
Okay, great. Thank you. Okay, so
Solid.
yeah, great. So remember what we showed at the very beginning, or earlier on. We showed that the null space is orthogonal to the column space of A transpose. Right? That's what we showed. The column space of A transpose. The null space of A is perpendicular to the row space of A, which is the same thing as the column space of A transpose.
okay.
Right? The null space of A is perpendicular to the row space of A. Right? Remember how we did it? We said, well, look. If you're in the null space of A, that means that this times U gives the zero vector. Right?
Okay.
This times, if you are in the null space, then you get killed by the matrix. Right? If you're in the null space, then the matrix sends you to zero.
Okay.
Okay? But what does that tell you? That tells you that you are perpendicular to each row. Right? If this is zero, what does that say? That this dot u, this vector dot this vector is zero. The second vector dot u, the same vector is zero. Right? You are perpendicular to every element in the row. So you're perpendicular to the entire row space
Okay.
of A,
Okay.
right? And so and the row space of A is the same thing as the column space of A transpose,
Okay.
right? Because, you know, right?
Yeah.
That's good. Okay.
All right.
Okay, so that's the first thing we showed, right? That the null space of A is perpendicular. Everybody in the null space of A is perpendicular to everybody in the column space of A transpose. Okay. Now what we're trying to show is that that the null space of A is exactly all those things that are perpendicular to the column space. Okay. It's not just that these guys are perpendicular, but they are all that's perpendicular. Okay, and so the first thing we need is to show that these guys are perpendicular. Well, they are perpendicular. We showed that, right? They are perpendicular. So everybody in here is contained in the set of perpendicular things, right? What we need to show is that that's all of them. Okay, that if we look at the things that are perpendicular to the column space, then it must be in the null space. Okay, so right, we're trying to show these two sets are equal. We have to show two things: that this one is contained in this one, and that this one is contained in that one. Right, and if we do that, then we see that these things are equal to each other. Okay, that's how one shows that. That's one way of showing that two sets are equal. Yeah, Mia.
So, so the null space like of linearly independent vector spaces is always just one vector?
Say it.
Never. So the null space is usually just one vector?
No. The null space is some subspace, right?
Okay.
Right. You have a matrix, and then you're looking at everybody who gets sent to 0. Right. That's a subspace. That's a subspace.
Mhm.
Right. You look at all x.
Yeah.
Right. The null space is all x that get killed by the matrix. Right.
But
It's some subspace.
But for like linearly independent things, it's just the 0 vector?
Yes, that's right.
So, okay.
Yeah, but we're not assuming that there's linear
Okay,
independence.
I was just...
Yeah, Teresa.
What's the difference between the C with the line under it and just this thing?
It's
You're
basically
not-
the same thing.
Okay.
Basically the same thing. People, yeah, basically the same thing.
And it means that it's contained within it?
It's contained within. Yeah, that every element here is an element. Every element of this set is an element of this set.
Okay, and it can
Like-
be written the other way too?
Yeah, yeah. So for example, like, you know, you students, right? You students are a subset of all humanity, right? Right. You students are a subset of all humanity. Right. The opposite is not true. Right. All humanity is not within this classroom.
And if there's no line under
It doesn't matter. It
Okay.
doesn't matter. Some people write it this way, some people write it this way. I think the line is included so that one can have this. One can also use this expression,
the... Okay.
right, to say contained in, right, contained in, but not equal to,
Mm.
right, to make it clear that this is just the proper subset, right, not just a subset, right. Okay. Okay, so okay, so that took a lot longer than I had hoped, right? So we're trying to show that that the null space is actually the orthogonal complement of the column space. Okay, the orthogonal complement of the column space of A transpose. What we've just recalled is that it's certainly a subset of it, right? The guys here certainly are in the orthogonal complement because they're perpendicular to everybody there. Okay, so now let's do the reverse direction. Okay, so we want to show that let me do it up here. So go backwards. we want to show that if x is in the orthogonal complement of the range of the transpose, then x is in the null space. Right? We want to show that the set on the right is contained in the set on the left. Okay. And this is also pretty straightforward. You say, well, if x is in the orthogonal complement of the range of the transpose, then of course x is perpendicular to the columns of A transpose. This is actually pretty trivial, I think. And so ax equals 0, right, the 0 vector. And that tells you that x is in the null space. So actually pretty So that's it. That gives you the fundamental subspaces theorem, right? That these things are perpendicular to each other. That these things are orthogonal. That this equals the orthogonal complement of that. One has a slight variation on it. If you substitute A transpose in here, equivalently, we put in A transpose here, we're going to get R A transpose. Right? That is to say that the null space of A transpose is the same thing as the orthogonal complement of the range of A. So you get this statement, which will be useful also. Okay. At this point, maybe it's like what's going on here, but you'll see soon that it's useful. Okay, that's it. That's it for today.